Welcome to the Explainer. When you're on a learning path in AI, you sometimes hit these concepts that just make everything click. Well, today, we're diving into one of those huge moments, taking our inspiration from Stanford's Deep Reinforcement Learning course to reflect on the elegant and powerful idea of Q learning. And this isn't just another algorithm in the textbook. As the lecture points out, this is arguably the one that kicked off the whole deep reinforcement learning revolution. I mean, the idea that you could teach an AI to master Atari games just by looking at the screen, that all started here. So yeah, let's get into it. So a lot of the time, we think about teaching an AI a policy, a direct strategy. But Q learning flips that on its head. It asks this really radical question. What if we didn't try to learn a strategy at all? What if we just figured out the value of every single move from every single position? Because if you knew that, the best strategy wouldn't be something you learn. It would just be obvious. Okay, so to really get our heads around this, the lecture uses this brilliant thought experiment. We're going to put the equations aside for a second and just build a real gut feeling for why this thing works so well. Okay, picture this. We've got our agent in this simple grid. It starts somewhere in the blue area, and its one and only mission is to get to that star. If it makes it, it gets 1 point. Anywhere else, nothing, 0. A super simple setup, right? Now let's give our agent let's be honest, a pretty terrible starting policy. Its entire strategy is no matter what, just move right. Now, from some spots, this might actually work, but from most places, it's just going to miss the goal completely. It's a bad policy, but hey, it's all our agent knows for now. Now, this is the key idea, the Q value. It's basically asking, if I'm in this spot and I take one specific action, and then I follow my dumb always right policy forever after, what's my total reward going to be? So think about it. If you're in a square right below the star, the Q value for the action move up is 1. Why? Because after you move up, the always right policy will eventually get you the reward. But the Q value for move right from that same spot is 0, because you'll just sail right past the goal. And here's where the magic happens. This is the big reveal. Once we've calculated all those Q values for our bad policy, we can create a brand new one. And the rule is incredibly simple. From any state, just pick the action that has the highest Q value. And here's the kicker. This new policy is guaranteed to be an improvement, or at the very least, no worse than what we started with. It's a free upgrade. And look at the result. It's fantastic. The old policy was a one-trick pony, but the new one is smarter. When it's below the star, it now knows the Q value for moving up is higher, so it moves up. Now, it's not perfect yet. It still has more to learn. But just by calculating values and picking the best one, we've improved our strategy without any complicated math. And you can probably guess, to get even better, we just repeat the process. Okay, that intuition is super powerful. But obviously, we can't do that loop by hand forever. We need a way to teach a neural network to find that ultimate cheat sheet of Q values directly. To do that, we need a rule, a mathematical law that defines what a perfect Q function actually looks like. And this is it, the Bellman optimality equation. You can think of this as our North Star. It's the rule of perfection. It says that for the one true optimal Q function, everything has to be perfectly self-consistent. The value of doing something right now must equal the immediate reward you get, plus the value of the absolute best thing you could possibly do from the very next state. If your Q function satisfies this equation everywhere, you've found the optimal one. You're done. So the Q learning algorithm cleverly turns this into a kind of supervised learning problem. Our neural network predicts one side of the equation, its current guess for the Q value. Then we calculate a target value using the other side of the equation, the immediate reward plus the best future value. The network's entire job is just to close the gap between its prediction and that target. When the gap is 0, our network has learned a function that satisfies that rule of perfection. Now, that all sounds great in theory, but in the real world, if you just throw a neural network at that update rule, things can get incredibly unstable. The lecture highlights 3 essential tricks that researchers developed to make this whole thing robust and effective. The first huge problem is that you're basically chasing a moving target. It's like trying to shoot at a bullseye that someone keeps wiggling around. The same network making the predictions is also being used to calculate the target it's trying to hit. So every time the network updates its weights, the target moves. It can cause the whole thing to just oscillate and never converge. The solution is simple but so effective. You use 2 networks. You have your main network that's learning all the time, and then you have a second target network, which is just a frozen copy of it. For a few thousand steps, the main network aims at the stable targets provided by the frozen one. Then, every so often, you copy the main network's newer, smarter weights over to the target network. It stabilizes the whole process. All right, the second issue is a bit more subtle. It all comes down to that max operation in the Bellman equation, where we pick the best possible next action. The problem is, the max operator is an optimist. Because of random noise in the network's estimates, it will occasionally see a high value for a bad action, just by luck. The max operator latches onto that noise, which leads to the network systematically thinking it's doing better than it really is. And this is where double DQN comes in. It's such a clever fix. It uses the two networks we already have, but for different jobs. We use the main, up-to-date network to select which action it thinks is best for the next state. But then, we use the old, frozen target network to provide an unbiased evaluation of how good that chosen action actually is. By decoupling the selection from the evaluation, you kill that overestimation bias. It's brilliant. So here's our toolkit. We solve instability with target networks. We fight overestimation with double DQM. And the third trick, end-step returns, helps the learning signal propagate way faster. Instead of just looking at the reward from the very next step, we look at the sum of rewards over the next, say, 5 steps. It gives the network a much richer, more accurate target to learn from. Okay, so we've got this powerful, battle-tested algorithm. So for you, as someone building up your own AI toolkit, the big question is, when do you actually pull this specific tool out of the box? The lecture gives this fantastic summary that I find myself coming back to all the time. While an algorithm like PPO is super stable and easy to use, and something like SAC is great for data efficiency, DQN and its variants are the absolute go-to for problems with discrete action spaces. We're talking about board games or the buttons on an Atari controller, up, down, left, right, fire. In those scenarios, DQN is often your most effective and efficient choice. So let's boil it all down. First, Q-learning cleverly finds the best actions without ever learning an explicit policy. Second, its foundation is the mathematical purity of the Bellman equation. Third, and this is crucial, it needs that pro-level toolkit, target networks, double DQN, to be stable in the real world. And finally, you know exactly where it fits. It's your go-to method for problems with discrete action spaces. This breakthrough was so much more than just an academic paper. It was the first real demonstration that an AI could learn complex human-level skills just from raw pixel data. It truly laid the groundwork for so much of what's happened since. The principles are still fundamental today, which really leaves us with a final thought. Now that you understand the engine, what are you going to build with it?